Hello everyone, and welcome to a deep dive into one of the most fascinating aspects of kernel optimization, fast system calls. Today we're unraveling how a seemingly simple function like getpid achieves incredible speed within the Linux kernel. Understanding these low-level mechanics isn't just academic, it gives you critical insight into building high-performance systems and diagnosing subtle performance bottlenecks. By the end of this lesson, you'll not only grasp the concept of system call overhead, but also discover the ingenious VDSO mechanism. We'll specifically analyze how getpid leverages this for optimization, and ultimately you'll appreciate the sophisticated strategies the kernel employs to keep things running blazingly fast. Let's get started. Before we talk about speed, let's understand the cost of a traditional system call. When your application needs to do something privileged like reading a file or getting your process ID, it has to transition from user mode to kernel mode. This transition isn't free. It involves what we call context switching overhead. The CPU has to save the current state of your user mode program and load the kernel state, then execute the kernel function, and finally switch back. For a function like getpid, which many applications call very frequently, this overhead can accumulate quickly, turning a seemingly trivial operation into a significant performance bottleneck. Imagine millions of calls, each incurring this small but measurable cost. It's a classic example of how frequent, small operations can add up to a major performance hit. To tackle this overhead for frequently called system calls, the Linux kernel introduces a clever mechanism called VDSO, or Virtual Dynamic Shared Object. Think of VDSO as a special memory page that the kernel maps directly into your application's user space. This page contains small, optimized implementations of certain system calls. The magic here is that because these functions are already mapped into your process's memory space, your application can call them directly, just like any other library function. This allows these specific kernel functions to be executed without a full context switch, dramatically reducing latency and boosting performance. So how does getpid specifically leverage VDSO? Instead of making a traditional system call, your application now calls a function like __VDSO getpid, which resides within that special VDSO memory page. This means there's no trap to the kernel required. The __VDSO getpid function simply reads the current process ID directly from a predefined memory location that the kernel keeps updated within the VDSO page. This direct access completely bypasses the costly context switch, leading to a significant latency reduction. For a function as frequently invoked as getpid, this optimization is a game changer, turning a potentially slow operation into an extremely fast user space execution. We've covered a lot today. To recap, the VDSO mechanism is a brilliant kernel optimization designed to make frequent system calls, like getpid, incredibly fast by mapping kernel functionality directly into user space. This effectively reduces the overhead associated with context switching, leading to substantial performance gains for applications that rely heavily on these calls. It's a testament to the continuous innovation in operating system design, pushing the boundaries of what's possible in terms of performance. So, consider this. How else might similar kernel optimizations beyond getpid impact the overall performance and responsiveness of complex real-world applications you might be building?